Start the recording.
Hello, I'm Kush Patel.
And I'm Yash Soni.
And this is our talk on the effectiveness and reliability of UVC sterilization for surface pathogens using 253.7 nanometer fluorescent tubes and 260 to 280 nanometer LEDs. We are associated with Arizona State University, and one of our co-authors, Vishesh Amin, is associated with the University of Southern California.
We are sponsored by Microdrop Diagnostics, SiO2 Innovates, and UV1 Hygienics. So a small outline for you guys is that the problem is the SARS-CoV-2 pandemic, or COVID-19, which created a need for safe, reliable, and fast disinfection. The solution we had was UVC at 0.2 to 0.28 micrometers, which dissociates DNA and RNAs, and which kills pathogens. The sources we used were fluorescent tubes and LEDs. The approach in quest was to find how stable and reliable are these UVC sources and which one is better at irradiating, fluorescent tubes or LEDs. The methods we used was to map the power density rho for 3 fluorescent and 3 LED sources as a function of geometry over 3 months. Our protocol was to measure the power density of 3 identical fluorescent and LED sources 3 times for 60 seconds every 10 seconds for a total of 63 samplings. We went to measure the pathogen kill rate in 2 minutes using InnovaBug. We use pathogen cultures at 72-hour incubation time and CFU counting to find this. The results we had were that the LEDs had a power density that varied with a plus or minus of 6.25% for 4 LEDs of 0.25 millimeters squared, with a kill rate of 99.99% at 1 centimeter.
Okay, so hold it. There's an error there. It's LED of 625 because it's 0.25 times 0.25.
Yeah.
And it's in centimeters square. So you need to fix that. So
625.
625
Right.
centimeters square. And then here, the protocol measure row of, and right there, every week.
Sorry, what?
Samplings.
The
protocol measure row of analytical FED, where we measured it like every 2-3 days. Let's say every 2-3 days, because that's what we did for 3 months.
Every 2 days. 2 to 3 days, yeah.
Every 2-3. So there was a weekend. Yeah. So that's important to understand that.
Yeah.
Right, because that's what we did.
Mm-hmm. Yeah.
Okay. So let's keep on going. So I took a minute here. So let's go.
So you just click that right there, like and then just move it like to the corner.
And don't forget to point to what you're talking about. It's very helpful.
Yeah. Okay.
Hello,
Ready?
I'm Kush Patel.
And I'm Yash Soni.
And this is our talk on the effectiveness and reliability of UVC sterilization for surface pathogens using 253.7 nanometer fluorescent tubes and 260 to 280 nanometer LEDs. We are associated with Arizona State University Physics Department, and one of our co-authors, Vishesh Amin, is associated with the University of Southern California.
Our sponsors are Microdrop Diagnostics, SiO2 Innovates, and UV1 Hygienics. So an outline is that our problem is the SARS-CoV-2 pandemic, or COVID-19, which created a need for safe, reliable, and fast disinfection. The solution we had was UVC at 0.2 to 0.28 micrometers, which associates DNA and RNA, thus killing pathogens. The sources we used were the fluorescent tubes and LEDs. Our approach in quest was to find how stable and reliable are these UVC sources, and to find out which one is better at irradiating pathogen, fluorescent tubes or LEDs. And the methods we used was to map the power density rho for 3 fluorescent and 3 LED sources as a function of geometry over 3 months of use. Our protocol was to measure the power density of 3 identical fluorescent and LED sources 3 times for 60 seconds every 10 seconds for a total of 63 samplings, which we took every 2 to 3 days. We wanted to measure the pathogen kill rate in 2 minutes using InnovaBug. We used pathogen cultures with a 72-hour incubation time and CFU counting. Our results were that the LEDs had a power density that varied with a plus or minus 6.25% for 4 LEDs of 0.0625 centimeters squared with a kill rate of 99.99% at 1 centimeter, while the fluorescent tubes had a power density that varied with a plus or minus 15% in a 10 centimeter tube with the same standards.
The problem we face is with the SARS-CoV-2 pandemic, also known as COVID-19 pandemic. It requires an all-time high need for safe, reliable methods of disinfection.
With the history of mankind came the history of the pandemic. With the 500-year timeline of these pandemics, as you can see, during even our inception, we always had pandemics and had a high death toll.
This death toll can be compared in this picture. The bubonic plague had a death toll of 200 million, and contrasting that with the SARS-CoV-2 pandemic, which has a death toll of 5 million and counting.
So our solution was UVC at 200 and 200 nanometers, where we dissociate the DNA and RNA strands, which thus killing the viral and bacterial loads of the pathogens.
Our question that we wanted to answer here is, what is the minimum UVC power density over an interval of 60 seconds to achieve a kill rate of 90 to 99%? And the answer is that for each bacteria, virus, and fungus, it is different. And it is not dependent on the size either. As we can see here, with the influenza virus that causes bird flu, it is 0.098 micrometers large, but it requires only 2.3 millijoules centimeter squared to achieve a kill rate of 90%. Similarly, contrasting this to the coronavirus, which is 0.113 micrometers, which is similar to size in that of the bird flu, it requires almost 10 times as much energy, requiring 23 millijoules per centimeter squared to achieve a kill rate of 90%.
So what we want to find was what controls the pathogen's energy threshold to reach a kill rate that is greater than 90% or 99%. As we've been showing, that is not required, it is not based on the viral, what the pathogen is and the size. So our answer was that the energy increases with the number of nucleic acid pairs in the pathogen's genome, where the more resistant to UVC antibiotic resistant E. coli requires 20 to 100 times more energy. An example is tetracycline, which has a computed energy for the kill rate of 90% as 53 millijoules per centimeter squared. Comparing this to the non-antibiotic resistant E. coli, which has a 2.6 millijoules per centimeter squared, this is a drastically large difference between the two. And as you can see, the gene survival ratio for tetracycline changes with the measured UVC energy for the antibiotic resistant E. coli, with 50 millijoules per centimeter squared having a gene survival ratio of 0.11 and increasing as the,
Could you just go over it again? I mean, it was a bit choppy because you had to think. So can you do it more smoothly now, you think?
Yeah. So what we want to find is what controls the pathogen's energy threshold to reach a kill rate that is greater than 90%.
And you want to connect with size. So if the size and the type of pathogen doesn't control the threshold, what does?
Yeah.
Mhm.
So
and we found the answer in the literature, recent literature.
okay. So if the size of the pathogen does not control the energy threshold, then what does? And what we found in the literature is that the energy increases with the number of nucleic acid pairs in the pathogen's genome. As
that are more resistant to UV.
Yeah.
Then, for example, you probably want to see put here, for example, this is to help you say it, because you know it's not just a mix. So put before antibiotic, for example. No, not there in that slide. That's yours.
No.
Right there.
Sorry.
So
that you have that question mark.
Mm-hmm.
So, and then put the more resistant behind the genome. So that way you don't chop it. Because you say it increases, it's a complex concept. Okay, no, just put for example there, FOR space EX. Okay, and then move more resistant to UV, put that next to genome, because then you'll read it when you say it. So cut and paste behind genome. Okay, and then move answer, remove the tab so it all fits in one line.
Yeah.
It's fighting you, just move the box. Move the box
Yeah.
to the left and then extend the box.
Yeah.
Maybe. You see on the right, pull that box out of the space. So you see the boundary, the box there. No, don't try to do that. Just pull the side of the box on the right. Bigger, 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 bigger. remove the arrow between answer and E. Okay, we finally have a one-liner. You absolutely want to avoid splitting sentences.
Mhm.
Okay, so then lower this thing because it's really crowding the orange line above.
Yeah.
This is to how you avoid crowding and chaos in a slide.
Mhm.
And then I would underline acid pair in pathogen genome. Acid pairs actually would move more resistant to UV behind the pair.
You may underline all this?
No. Just move more resistant to UV behind acid pairs.
Okay. Oh, behind it.
Paste.
Yeah.
And then, no, behind the pair.
Oh my God. Okay. Yeah.
Behind the word pair. I'm trying to put correct grammar and more natural to say. You tongue twist it because it's poor writing. Put pairs, UV pairs in front. No, I'm just going to go nuts here. Energy increases with number of nucleic acid pairs more resistant to UV. So take the word pairs, put it behind acid. Call them bonds. It's more, okay, uppercase bonds, uppercase. The whole thing, bonds, uppercase, the whole bond.
Okay.
So what I'm trying to say here, we have a molecular level inside. Oh gosh, what is this now?
It's on a space.
Just stretch the box. How much more does it need?
Okay.
Yeah, there we go. It fits. Just move it a little bit so you have between the boundary of the slide. So move a little bit the box towards the left, not the right.
Yeah.
Okay, good. Okay, so the key point is what controls this energy threshold if it's not size and the type of pathogen?
Yeah.
It is the number of nucleic acid bonds that can resist to UV in the pathogen genomes. What it really means is that the bond of some nucleic acid pair is much stronger than other nucleic acid pair, molecular bond. And so boom, they don't break up and you need a higher amount of energy to break the bond. So that's pretty intuitive, right?
Yeah.
And it's been proven, and we can compute the energy and we can compare to the result. We live in extraordinary times. I'm totally amazed we can do that, but we can. We can compute the UV resistance of any pathogen, provided we got the genome sequence, which is another can of worms, but we're getting good at that.
Can we present?
Okay, so do you want to take a break and move on, or you're ready to do it?
We're ready.
You're ready.
Okay, I just don't want to stress you. Okay, let's go.
So if size does not control the energy threshold, then what does? And our answer is that the energy increases with the number of nucleic acid bonds that are more resistant to UV in pathogen's genome. For example, the antibiotic-resistant E. coli requiring 20 to 100 times more energy. Example,
And
this
E. coli, the coli has disappeared.
where?
Typo. Antibiotic-resistant E. coli requires a 20 to 100 times more energy. Just write energy because you have the E. coli.
You've got 2 minutes left.
More energy than E. coli. And then just put the E. coli in italic.
Yeah.
Okay, E. coli in italic. It's Latin. But
Yeah.
put also antibiotic resistant, because the point trying to make is that that's the difference,
You want me to underline this?
I guess. Yeah. Okay. Very good. Okay, so take it back from the top. Sorry, I'm getting, it's just,
Yeah.
it's just my throat is.
Yeah. So if size does not control the pathogen's energy threshold, then what does? The answer is that the energy increases with the number of nucleic acid bonds that are more resistant to UV in the pathogen's genome. An example of this is antibiotic-resistant E. coli requiring 20 to 100 times more energy than E. coli. As you can see here, tetracycline requires a computed energy for a kill rate of 90% at.
But you have to say tetracycline resistant E. coli, not tetracycline.
Okay, okay, my bad. Tetracycline resistant E. coli requires a computed energy for a kill rate of 90% to be 53 millijoules per centimeter squared. Comparing this to non-antibiotic resistant E. coli, which is at 2.6 millijoules per centimeter squared, we can see that there's a stark difference between the two. And as you can see here, the gene survival ratio versus the measured UVC energy for antibiotic resistant E. coli is that the gene survival ratio is 0.11 for a measured UVC energy at 50 millijoules per centimeter squared.
The approach we used is to answer two key questions. How stable and reliable is the power density in the UVC sources? And how does stability and reliability depend on the type of UVC sources? We also wanted to see the efficacy of the rapid 60-second disinfection period and to see if we could reach the minimum energy threshold to achieve a minimum kill rate of 99.9% for the pathogen of concern. Our design of experiment was that we used two types of sources of 3 units each. We used three identical fluorescent tube wands of 253.7 nanometers, which were FDA and EPA certified, and we used 3 solid-state LED domes from 260 to 280 nanometers, which are more compact and use less power. The key comparison we wanted to make was how effective are each at disassociating DNA, RNA, and killing pathogens.
So the method in our design experiment was that we used 2 types of UVC sources with 3 commercial units each. We used 3 identical fluorescent tubes, which were quartz tube wands, and 3 solid-state LED domes.
All right, Dennis, thank you very much.
We want to
If people have questions, they can go ahead and type them in the Q&A box below the talk. In the meantime, yeah, I was going to ask you, you have really diverse set of skills among the students in your labs. And so I don't know, if you were a physics student interested in this, what kind of...
And we want to compare the power density between the fluorescent tube and the LEDs using a gallium nitride detector. As you can see here, we use a control geometry, and we also found that the UVA and UVB are drastically different in sterilizing surfaces, as the UVB and UVA are basically non-usable.
Yeah, but I would just emphasize that we're also considering that the distribution of UVC is quite different in a fluorescent tube.
Yeah,
It's just a single wavelength. So don't go UVA, skip the UVA, UVB. They can read. They can look at it on screen.
Okay.
But what really matters to your experiment is that the fluorescent source is basically almost a single wavelength, while the solid state source is a range.
Okay.
And how is that going to affect the sterilization efficiency?
So what we found is that the LEDs had a range of 260 to 280 nanometers, but the fluorescent tube had a 253.7 nanometer.
Right, thanks. This was a really interesting talk. And it's really great to see the progress. There's clearly major advancements going on in this area just in the past couple of years. So
the results for stability of power density over 60 seconds measured at 10-second intervals was that the fluorescent course tube one had an average power density of 2000 with a relative fluctuation of 5% over a 50-second interval, while the LEDs had an average of 1300 microwatts per centimeter squared with a relative fluctuation of 3%. And each LED's power density average was 56% of that of the fluorescent tube wand.
So very similarly to the dome number 1, dome number 2 had an average power density of 900 with a plus or minus of 17 microwatts per centimeter squared with a relative fluctuation of 2%. We use the same control geometry to find dome number 2.
Can you see my screen now?
I can, yeah, it's not in full screen mode, but yeah.
Is it okay?
Yeah, that looks good.
Okay.
All right.
So
for the results, we wanted to see if our experiment was reproducible over time. So we repeated the measurement a month later for dome number 2. And we found that the average power density went from 900 to about 890, yielding an 11% difference. And about the LEDs, we measured the center spot between the 4 LEDs, which yielded 183 microwatts per centimeter squared, which is 20% of the LED's average power density.
So the results we found with the 4 LEDs is that before UVC, we had a greener image, with the green representing the DNA and RNA of the pathogen. Well, after UVC, we had a more blue image with less fluorescence from the DNA and RNA of the pathogen. So with the comparison using color intensity integration, we found that there was a 30% difference and less of green and 175% more blue. So the intensity of the green was 1 before UVC, but the intensity of blue was 0.37 after UVC, which yields a 99.99% kill rate.
For our conclusions, we found that the solid state LEDs were more reliable than the fluorescent tube after repeated use 1 month later, with an 11% change in the power density of the LED and a 30 to 50% decrease in the power density of the fluorescent one. And the stability of the LEDs, the power density varied about 6.25% in the 4 LEDs of 0.25 millimeters squared and the kill rate of 99%. The fluorescent tube, however, had a power density variation of 15% in a 10 centimeter tube, achieving a kill rate of 99.99% at 1 centimeter. The minimum energy UVC threshold varies by pathogen and DNA RNA UVC resistance by a factor of 10 to 100 due to the difference in nucleic acid bonds. And finally, the UVC sterilization via LEDs was the most reliable form of pathogenization in both bacteria and viral loads, which will help minimize pandemic spread.
Thank you for listening to us.
Okay, so I think you have it. So go back to conclusion. Now, I wanted you to show the dead pathogen from slide 3, because the point you want to make is that it's not good enough to have the energy you think you have. So go to 6, go to 6. Click on the black box and ungroup it.
This whole black box?
Yeah. Accurate. Maybe it's ungroup. Just click on the little circle there and click on the dead pathogen, the little X.
Yeah.
Click on the X2, combine the two. Can you do that?
I think it's already grouped.
Okay, copy. Okay, and then go down. Because the punchline of your conclusion, okay, put that little pathogen at the kill rate there. Shrink it a little bit. No, don't remove the other one. What did you do?
I thought you wanted me to replace.
No. Okay, go back. Leave that pathogen there. I'm going to explain the ID. Okay, then put the other one there with the little cross eyes.
Oh, because she added the cross eyes with a text box.
Yeah. Yeah. I'll have to.
Okay, the point you want to make is that it's not enough to tickle the pathogen and do some damage.
Yeah.
Mm-hmm.
You have to kill it. Make this a circle, please, not an oval.
Mm-hmm. That good?
So, and so you cannot deal with fluctuation of 30 to 50%, number one. You know, just insert text and put 2x. It's not that hard.
Yeah.
All the pros and cons of politics exist. There's a really urgent need.
XX. Yeah, then this decrease the size. It's important you have pictogram.
Right, yeah.
Okay, make it bold.
Undo, yeah.
You deleted it. Okay, bold.
Yeah, I'm just making them the same size.
Move it up above the mouth. So
yeah.
You know, you can just click up with your cursor. I know you don't have experience with Excel, with PowerPoint. Just stick with PowerPoint. Do not use Google Slide. Do not use Google Doc if you want to be a scientist.
Okay.
It's CRAP for low-level third-grade use and middle school, high school paper.
Yeah, the only thing is that Google Slides allows you to collaborate more.
No, it doesn't. I've used Google Slides. It was a disaster. There was no backup. I explained that. So somebody in the group would delete something. We didn't have a copy of it. And then when I had 3 or 4 students working at the same time, it would hang up. And then your Google slide lost half of the Greeks. We need Greek letters to do science, blah, blah, blah. So now we tried all summer of 2020, and a group of 20 students at a time and me agreed we failed. No Google slide, period. You're not saving money by using junk software, free software.
Mhm.
Besides, this is going to get proprietary and Google can read everything in your slide. So scrap that.
So we always have a nanopore that's aligned. You can see the 2 electrodes that's aligned.
Yeah, sounds
Cool.
good.
So I
in
think you
between
are within
the,
10 minutes. I think that
Yeah.
you guys
between
need a
the
break.
two,
Mhm.
dielectric layers
So,
of
you
silicon
know, just
dioxide. And the
take a
nanopore
break,
is formed in
eat,
between
drink,
the two
go to the
electrodes.
washroom, and
Okay,
then you
yeah.
can just run with yourself, and then we'll
Has
reconvene.
the
Did
opportunity
you talk at
to
1 o'clock?
measure the
Ours is
difference
at
in
12:48.
12:48.
and as well as transverse.
But we should
Oh,
be
you
there by
didn't-
12:48.
Okay,
The
suggestions from
observation shows
Mark,
that
which
the
is much into
electrodes which are in
chocolate.
blue are aligned, and then
If you don't feel
the
like
thickness of
eating,
the
having
nanopore,
chocolate,
which is
because
at the
it
middle
boosts
of
your
the,
glucose level without giving you a
active
sugar high.
electrodes are defined by the
Mhm.
thickness of
I mean,
the
Okay.
Belgians have
nanopore
been using this for
in
years,
yellow,
and it
uh,
just makes you happy
which
in a
is
good
around
mood. I'm gonna have some
several-
chocolate right now.
couple of,
All right, thank you.
10 or
Thank you.
20
Okay.
nanometers.
See you at
And
12:48.
this part
Yeah,
is
wait, should we leave?
later in order
Yeah,
to
Because
form
when, if you're gonna watch it on the Zoom and you're unmuted, then the audio will come through on your Zoom also, and it'll come through on our
yeah,
presentation.
we should have seen. Okay, thank you. We're gonna leave.
important because otherwise
Okay, thank you.
aggressive
Okay.
growth of the electrodes along sides, and that is not a very suitable measurement scenario for high resolution sensing. Going through the fabrication protocol that we use to give a quick picture, we deposit the chrome metal, which is going to be the cavity leader on. We etch the we make trenches on the both sides. That is going to be the chamber, the cis on the left and the trans on the right. The DNAs will be lodged and will be driven to the other side. We deposit aluminum metal on the trenches. Then we lay out our electrode, which we are seeing at the cross-section view. So you can see the electrodes are actually going into the screen. Then we lay our dielectric, silicon dioxide, 100 nanometers of that. Then we form the pillars, which actually acts as passivation, passivating the electrode region, and also forms a mask where we can etch the silicon dioxide part that's open in order to open up the surface area of the aluminum part to etch selectively later on. So we remove the silicon dioxide, then we form a covering on the top to form it as a closed macrofluidic device, and then we etch selectively using wet chemical etching of the aluminum and the inner chrome. And you can see that's how, if we lodge the DNA on the left chamber and drive it across the cavity, the nanopore, it will reach the other side through a nanopore. So once the device has been done, we bond it on the PCB board. We set up our electronics. We connect it to the tubes, the macrofluidic reservoirs, and the last one is the setup for the electronic circuit that we use. So we have two measurement setup. One is measuring the tunneling current, applying a tunneling bias or a voltage to measure the tunneling current. And the other one is the ionic, which is measuring the ionic current by application of another driving bias connected to reference electrodes. Now, this is an important thing that we have installed in our device, installed in our measurement techniques, which is actually going to fine tune the nanopore device to the exact tunneling current distance that is suitable for measurement of the DNA translocation or detection or sequencing. So we use our program, which measures the impedance in between the tunneling electrodes, and it sends initially when the electrodes are far apart, it sends a pulse form of reducing potential and deposits gold on it. You can see the GIF, the deposition is happening. And then when a certain quantum conductance is reached, the program sends oxidation potential to open up the gap. So in this way, we can see that the gap actually can be closed and then open, and quantum conductance can be reached. So we do a multiple times of opening and closing of the gap so that we have a very stable conductance. Hello?
We've got 2 minutes left.
Okay, yeah, I'm passing it up. Then talking about the electrochemical deposition, we actually do some characterization. We know the chemical species. We try to see the pulse potential is actually suitable as scanning potential. We see the overpotential importance to have a particular potential that is going to give a grain size that's smaller than the cavity, so we can have a 2D isotopic growth. Okay, talking about the main thing, that the DNA detection that we have detected in our with our device. Before the DNA is lodged into the cis chamber, we flow the chamber overnight with PEG thiol to reduce the interaction of DNA with gold. So PEG thiol can bond with the gold and do not let the DNA interact. But we have found the evidences of actually lambda DNA translocation happening. A blank test with PB and a negative bias shows no current. DNA is lodged in cis with a positive 50 millivolts shows no current, and DNA in lodged in cis with a negative bias 50 millivolts shows current, shows detection of events related to translocation of DNA. And the fluorescence image also shows that. We have seen that 50 millivolt actually shows correlated, more than 80% of correlated event related to ionic current and tunneling current, and they're all telling us that the correlated events are because of DNA translocation. There are a few characteristics of the detected events. We have also seen that 3/4 of the transverse events were not correlated. You can see that the correlated transverse currents shows high current and a smaller peak wave, which is spread over a region. So this is what we think is that the transient currents caused because of electroosmotic flow of the charges near the double layer that hinders the flow of the DNA. But they actually go the other side from cis to trans, and we can detect as a correlated current in transverse current. But the current is high, so we have to address that. The current is high is it because of the transient event that is happening near the nanopore. And we also see uncorrelated event, which has a much lower current, but it's spread out, the peak wave is spread out. We think that those DNAs were not able to go from the cis to the trans, but they were moving near the electrodes and they could not bond to the electrode surface because the electrode surface was modified with PEG. So that's why we have a low current, but it could never make it to the trans site. Then we have observed another thing is that we have observed that when we apply a negative 50 millivolt, we see events. Then we apply a very high voltage like negative 200 millivolt, and we do not see event happening. Then we again apply negative 50 millivolt, and we see 5 times higher event. So we think that when we apply negative 200 millivolts, it was either the detection was beyond the bandwidth of the device we have, or the negative 200 millivolt actually made a lot of DNAs enrich or accumulate in the cis site. And as soon as we applied a negative 50 millivolt, those were actually drawn to the other side. And that's why we see so many events that is much more than when we just apply negative 50 millivolt. So DNA enrichment in the cis chamber is actually a thing that we have observed. And going back to positive 50 millivolt, after this, we see no DNA events. So we are sure that the DNA events are due to the events that we see are because of DNA going from the cis to the trans chamber. And then lastly, we see another thing is that we apply a negative 200 millivolt high voltage, then we remove that potential, and then we see, then we give no potential, is almost 0 volts. And then we see now that we see that there are forward events and there are backward events. The forward events are in red and backward events are in green. This is related. Hello. But we think that the forward events are caused because the electrons, the DNAs were enriched in the cis, and after it was removed, they flowed to the trans chamber. But there might have been some DNA already went to the trans chamber, and due to the residual voltage potential that is there.
Please try to wrap up. You've gone several minutes over.
Okay, yeah, I'll do it in 1 minute. Because of the, there would be some residual potential between the reference electrodes that they have been drawn from the trans side to the cis side, and that's why we see a backward event. But what we do not understand is that in both forward and backward event, the ionic current should have been in opposite polarity, but the tunneling current should be always positive, but we see a negative side. And then we observe that the forward current, ionic current is always leading ahead, it's faster than the backward event because forward current is driven, already there was enrichment in the cis side and it goes to the other, whereas the DNAs in the trans side, they were opposed by the the transient motion of the charges near the charge double layer that might have obstructed it and made it slower. So there are more challenges to address. There there's need to reduce the effect of transient signals so we can actually detect the, we can make sure the tunneling current that we see are true because of the interaction of the DNA. So we need to really slow down the DNA. And we can do that in many ways, like transverse electrode can be tweaked to slow down DNA, and we need to surface modify the electrode surface. So in summary, our electrochemical deposition technique actually improves the quality of nanopore. We have successfully aligned the nanopore with the tunneling electrodes, and we have detected DNA motion, and more than 93% events were correlated, so which is telling about the detected events of DNA moving. And I would like to acknowledge our crew members and my advisor, and then the support from the Air Force Office of Scientific Research and facilities in Arizona State University. Thank you.
Great, thank you very much. You've gone over time, so I think we don't have time for questions, and we'll move on to the next talk. But thanks for this interesting, very interesting research. It looks like you're making a lot of progress there, and we'll move on to our next talk from Seo-Yeon Choi. All right, we can see your slides and you sound okay.
Okay, I'll begin my presentation. Hello, I'm Zhang. Right now, I'll be presenting on thermodynamic analysis of nanoparticles for the treatment of neurodegenerative disease. This is the sequence of the presentation. Now I'll move straight on to the introduction. Alzheimer's disease is a common neurodegenerative.
Can you tell us if you're a student or not a student?
Am I a student?
Yes.
Yes, I'm a student.
Are you a graduate student or an undergraduate student?
Oh, I'm a high school student.
High school student. Okay, thank you very much.
Okay, should I continue? So Alzheimer's disease is a common neurodegenerative disease, and although the etiology of AD is largely unknown, it is found to be highly correlated with metal-ion imbalance. Metal-ion imbalance promotes amyloid beta overproduction or causes tau hyperphosphorylation, which could lead to neurodegeneration. To counter metal-ion imbalance, chelation therapy have been proposed. Moreover, one of the characteristic hallmarks of Alzheimer's disease is amyloid plaques. And to counter this, photodynamic therapy have been proposed to inhibit amyloid beta aggregation and to counter Alzheimer's disease. In this paper, we aim to utilize computational tests to assess the properties of nanoparticles that have the potential to be used in these therapies as photosensitizers or chelators. Next, I'll talk about our theoretical background. The first is photodynamic therapy. In PDT, light between a certain frequency is used to activate the photosensitizer, which then transfers energy to molecular oxygen, resulting in the production of reactive oxygen species. These ROS can oxygenate amyloid beta monomers and greatly reduce amyloid beta mediated neurotoxicity. There are several nanoparticles being studied to be used as photosensitizers, including porphyrins, chlorine variants, and phthalocyanins. Porphyrins contain 4 chiral rings linked by the methane carbon bridges, as you can see on the picture on the right. It can be reshaped by chemically modifying their side chains or by substituting centrimetal ions or by adding CNTs. As for chlorine variants, they're formed by the reduction of 1 or 2 of the peripheral double bonds in porphyrins. And phthalocyanins is also closely related to porphyrins. They contain 4 indole units, as you can see on the picture on the right. Next, I would like to talk about chelation therapy. It is a chemical technique that removes heavy metals and or minerals, for instance, lead, mercury, copper, etc., from the body by injecting a synthetic solution into the bloodstream. These heavy metals or minerals are grabbed by chelators and therefore removed. Some of the molecules being studied to be used as chelators include EDTA and TTPA. Out of these two, EDTA is the most commonly used. I would also like to mention several biophysical theories. First up is optimization energy. So the process of energy optimization is basically developing a spatial arrangement for a group of atoms in which the net interatomic force on each atom is acceptably close to zero. Therefore, we can find the most stable geometry of the molecule using this process. In general, reduced optimization energy leads to greater thermodynamic stability or chemical stability. However, we need to note that comparisons between optimization energy only functions within the same group of molecules. For instance, molecule AAA can only compare to other AAA-1 or AA-2. Second is the dipole moment. It is the measure of the polarity of a compound caused by the differences in electronegativity between atoms or ions. It correlates with the conductivity of a molecule. In the case of photosensitizers, being nonpolar is better since it facilitates the movement of these molecules across the lipid membrane. In the case of chelators, being polar is better since it needs to grab metal ions. Lastly, I'll talk about EPM. It visualizes charge distribution, charge-related properties, and the sizes and shapes of molecules. Red regions in EPM coincide with lower electrostatic potential energy, which means they're negative. Blue regions coincide with higher electrostatic potential energy, when they're positive. I'll move on to materials and methods. So I basically used this computer software Avogadro, which is an open source molecular editing program with an auto optimization tool that enables the calculation of the theoretical values of a chemical structure's atomic and biochemical properties. Basically, this is what I did. We are taking, for instance, CO2. I just modeled the molecule using the auto optimization tool. I optimized the molecule and find the most stable geometry. I can view the optimized energy and estimated dipole moment using this molecular properties panel through the computer's calculation. I created surfaces using the function in Avogadro, create surfaces. I could create these electrostatic potential map. As you can see, the blue regions correlate with the positive regions and the red regions indicate the negative regions. These are the molecules I modeled: EDTA and DTPA for chelators, porphyrin isomers, metal-porphyrins, and metal OEPs, chlorines, metal-thiocyanins for photosensitizers. I'll move on to resulting discussion. Firstly, we compared EDTA and DTPA for chelators. The table shows the results. We need to note that since EDTA and DTPA are not molecules with a similar number of bonds, their optimization energy cannot be compared. So we compared the dipole moments. We found out that EDTA had higher dipole moments, indicating higher conductivity. And therefore, we concluded that EDTA is more suitable to be used as a chelator in terms of the dipole moments. Observing the EPM, we saw that the charge distribution was similar in EDTA and DTPA. It was a little bit predictable since the inside regions, there are hydrogens, so they're positive. The peripheral regions, mostly negative because of oxygen. Next, we observe the metalloporphyrins. Next, we also observe the porphyrin isomers, the following 7 porphyrin isomers. Excluding the isoporphyrine, the molecule we see right here, optimized energy remains in the range of 650 to 850 kilojoules per mole. Porphyrin had the lowest optimization energy, which is concurrent with the previous literature. Porphyrin also had the lowest dipole moment, followed by corphysine and hemicorphysine, as you can see from the graph. However, we noted that N-confused porphyrins and doubly N-confused porphyrins had high dipole moments, in fact, higher than water, meaning that they may be less efficient in crossing lipid membranes when entering the cell. Therefore, we concluded by observing the optimization energy and the dipole moments that porphyrin, corphysine, and hemicorphysine were the most suitable to be used as photosensitizers. Observing the electrostatic potential map, we saw that the distribution of electrons was similar except for N-confused porphyrin and the doubly N-confused porphyrin. The red regions occurred because of nitrogen and blue regions because of hydrogen. We saw that the color of the electrostatic potential map was not that deep, so the polarity was not that, the electronic distribution was not that polarized. As for metalloporphyrins, we observed the following 6 metalloporphyrins with 6 different central metal ions. In terms of optimization energy, iron porphyrin and calcium porphyrin were the most stable molecules. Zinc porphyrin and aluminum porphyrin, the 2 metals that are frequently used for photosensitizers, were found to have the highest optimization energy. Dipole moments were 0 or low for all molecules. And since we saw that the dipole moments were 0 or low for all molecules, we concluded by comparing the optimization energy that iron porphyrin and calcium porphyrin were the most effective photosensitizers. Observing the EPM, we saw that zinc porphyrin, copper porphyrin, and iron porphyrin is strongly positive over the whole central region. Although the dipole moment is low, this could affect the interaction of these molecules in the body. We also observe metal OEPs or octavioporphyrins, which is another type of metalloporphyrins. We use the same central metal ions as before. Observing the two graphs, we saw that because of the number of bonds, optimized energy was generally higher than that of metalloporphyrins, but the tendency of the optimized energy, dipole moments, and EPM were all similar to metalloporphyrins. I'm sorry, I don't know why, but the slides are just moving on. I didn't click on the slides, so I'm sorry for this. Yeah.
Okay, you have about 2 minutes left.
Okay. So observing the EPM, we also saw that this, the electronic distribution was similar to that as we've seen in the metalloporphyrins. Third type of molecules that we studied for photosensitizers were chlorine variants. We studied the following 3 molecules. They all had similar optimized energy within the range of 655 to 665 kilojoules per mole. Bacterial chlorine out of the 3 had the lowest dipole moments, so we concluded that it would most likely to be effective in terms of the dipole moment. Observing the EPM, we saw that all of them had negative regions concentrated on the center and positive regions on the periphery. The last type of molecules that we observed were metallophthalecyanones with the 9 central metal ions as the following. Generally, the metallophthalecyanones with transition metals with haplo 3D shells, iron, manganese, cobalt, nickel have low optimized energy. However, according to previous literature that we have found, they are less capable of generating singlet oxygens. In fact, the order of generating singlet oxygens is the following as shown. So considering the generation of singlet oxygen and optimized energy, we concluded that magnesium phthalecyano would be the most suitable photosensitizer in this case. For the EPM, we saw that except for AOPC, aluminum, and magnesium, as you can see here, other molecules showed a similar distribution of electrons in the EPM with the positive regions in this with strong positive regions in the center. We again noted that this could affect the interactions of these molecules in the body. This is the summary of my paper of our research. As for chelators, conductivity-wise, EDTA was shown to be better than TTPAs. As with photosensitizers, we saw that porphyrins, porphysine, hemiporphysine, iron porphyrin, calcium porphyrin, bacterial porphyrin, and magnesium phthalecyanones were the most effective photosensitizers. Thank you.
Great, thank you very much. If there's anyone in the audience who has any questions, the Q&A. Yeah, I guess I'm wondering, so where does this go next? For example, for like the chelators, you saw that one seemed to be a better candidate than others. So is there any more you would do on that?
I'm pretty sure that I'll be able to continue my research using other types of molecules. There are plenty of molecules that are being studied to be used as photosensitizers or chelators. So I'm pretty sure that I'll be able to continue my research in a similar note, observing the EPM and the optimization energy in the dipole.
All right. If there are no other questions, thanks again for your talk. Very interesting, very impressive work. Yeah, we'll move on to the final talk in this session from Yash Soni. I can see you. Can't see your slides yet. There we go. Hi, we can see you. Would you like to share your slides?
Yeah.
Mhm.